Okay, so we're going to have a look at another question. This comes from the 2020 HSC Advanced Maths paper, and this is the last part of the last question. So this is question C. Find the rate of change of the mice population when the cat population reaches a maximum. So we're going to need to do some derivatives for this question. First, we need to find the derivative of the cat population. And we have the mice population here and the cat population here. So dc of t dt, here we have minus 80 cosine. So the 120 will go away. Minus cosine becomes positive sine. So we have 80 sine pi on 26 times t minus 10. And then we're going to multiply this by the derivative of the inside. The derivative of the inside here is pi on 26. Pi on 26. So here we end up with 80 times pi on 26, that's 40 pi on 13, multiplied by sine of pi on 26 times t minus 10. And this is our derivative. Now for the cat population to reach a maximum, we need the derivative here to be equal to 0. So let's solve this. This is sine of pi on 26 times t minus 10 is equal to 0. Now when is sine equal to 0? Sine is equal to 0 at 0, pi, and 2 pi. So this means we have pi on 26 times t minus 10 has to be equal to pi k, such that k is included in the integers. And in fact here, the only integers we're allowed to have are 0, 1, and 2. So we're just going to solve this. We're just going to let k equal 0. And we will find that t is equal to 10. So this is our first result. T is 10 is a minimum or maximum. If you recall from the cosine graph went down to begin with because it's a negative cosine. So this is actually a min. So this is not the time value we want. So we need to let k equal 1. So we get, so this was all k equals 0. Now we've got k equals 1. So we have pi on 26 times t minus 10 is equal to pi. Multiply both by 26, divide both by pi. We get t minus 10 is equal to 26. Add 10 to both sides. This gives us t is 36. And we know that this has to be the max. Because the period is 52, so a full cycle happens over 52 units. 10 is the minimum. The maximum must be half of 52 many units away, so this is 36. We're able to calculate it here, but intuitively you could have got it either way. So this means the cat population reaches a maximum when the time is 36. Now we need to find the rate of change of the mice population when the cat population reaches a maximum. We actually need the derivative of the mice population. So we have mt up here. Sine becomes cosine. The 20,000 on the end goes away. The derivative of the inside is pi on 26. So this will be pi on 26 times 15,000 cosine pi on 26 times time. So dm of t dt will be equal to pi on 26 times 15,000 times cosine of pi on 26 times time. Now we have to let time equal 36. This gives us pi on 26 times 15,000 times cosine of 36 pi on 26. 36 pi on 26. Now this is not going to simplify nicely And consequently, this is actually the exact answer. Right? So in terms of exact, we could simplify the 15,000 and the 26, so we could make this 7,500 pi over 13 times cosine. 36 and 26 are both divisible by 2, 18 pi on 13. This is the exact solution. We could also put this in the calculator and numerically approximate this. Now we have to make sure we're in the right mode. So we get 7500 times pi divided by 13 multiplied by cosine of 18 times pi over 13, and this gives us minus 642.706. Minus 642.706 dot 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 dot. This is about minus 642.71 to 2 decimal places. And this is dm dt evaluated when the cat population is at a maximum. And this number essentially makes sense. We expect that as the cat population is at its maximum, the mice population should be decreasing quite quickly. So a decrease of 642 mice per unit time, that's quite a lot. That's almost 1,000, given that the amplitude is 15,000. A change of 642 per unit time is quite a lot. Right? So we're expecting quite a steep decrease at that point. That's what we got here. In this question, there's a few ways to do it. If you do it algebraically, you'll get 1 mark for the working. So there'll be 1 mark just allocated to a whole heap of working that essentially gets you the answer, but doesn't get you quite there. The second mark will be the remainder of the working, and then the fact that the derivative at that value is minus 642.71. If you use the graph, you could in theory use the graph. It's not a good idea in this question. If you did use the graph and you sort of measured the tangents or stuff like that, it's in theory possible that you get a number like this. It's just too precise of a number to really be getting properly, especially because the graph is not going to be perfect. But certainly the working will look something like this. You're taking multiple derivatives, you're solving some of them under certain conditions, and then simplifying them and getting to a particular solution. So this is the answer that we're after, and this is what the marking looked like.